I'm a software engineer on Facebook Presto team, and today I want to talk about a recent optimization we did, which is common sub expression optimization. So the motivation is kind of like, we've seen these kind of queries a lot in production. Like, I don't know about other people. People in Facebook here loves using JSON because it's very flexible. You can basically change the data without changing schema and everything. But unfortunately, JSON is a very expensive operation in terms of database data manipulation. So people try to kind of do a better job. So they don't just do JSON parse and JSON extract all the time anymore. They try to do JSON parse and then cast it to a row type, and the row is actually quite performant. The query, so this is actually like a small part of like a real query that I masked out a lot of the names and stuff. The actual query actually have 9 JSON parts. The whole query is like probably 100 lines or something, and there's like a complex manipulation after that, but those are all quite efficient. The problem is there's 9 JSON parts, and in this example, there's 6 JSON parts, and they are separate. They like how currently Presto works, or like how previously Presto works. The same expression is going to be evaluated 6 times or 9 times in the original query. And JSON parse is very expensive. So as a result, the query performance is terrible. So if you look at the execution plan, you would see that for this project, this looks even more weird because try-cast doesn't really print out the output type. So it looks exactly the same for repeating 6 times. But actually the common sub-expression here is JSON parse features. And we're casting it to different types. That's why there are 6 different expressions. So obviously we don't want to run like these 6 times, especially if it's expensive, right? So what can we do? So the solution, well, obviously we want to run it only once. So it's just how to do that, right? So we want to do common sub-expression optimization, which means we want to extract the common sub-expression among all the projections and run that only once. So how it works. So first, let's kind of roll back to how projection works in Facebook, in Presto before CSE. So basically, there are kind of like 2 sides. One is when we are processing the query, there's a class called page function compiler, and it actually compiles both projection and filter, but we're talking about projection here. So the input, you will see that it's a list of projections. In this case, it's 6 try-cast JSON parse features. The page function compiler takes this, and for each projection, it would generate bytecode. It will basically generate a class, generate a Java class that's like at runtime, you will be able to call this class to actually evaluate the projection and get the results. We are iterating through all the projections and generate 1 class for each assignment, basically. So for this example, you would end up have 6 different classes. Once you have these all compiled and generated, and at runtime, the project operator would take a page and try to invoke these functions on a given page, and then write the output to the output page. So it would see the first projection is taking these input and write to the first column of the output, and the second would be processed and then write to the second column, and vice versa, and like going forward until the 6th one in this example. So now we can see the problem here, because there are 6 separate classes, and they basically don't share any common code path. That's why, like, even though intuitively people might be thinking that we're actually doing it, we're not, and it's it needs actual like refactoring to be able to do this. So yeah, that's basically what we did. And so first thing we did is we basically say that, okay, we cannot generate one class per projection. Let's try to take these all these expressions as a whole and analyze them and generate a page projection that can produce multiple outputs instead of only one output. And so inside it, this is how it works. So first, when we take all the projections in, we'll try to analyze and extract all the common sub-expressions. And we're gonna, after we have all the set of sub-expressions, we'll divide the projection by groups of common dependencies of the sub-expression. So in the given example, basically, what we have is, well, all the projections depend on JSON parse, which is the common sub-expression. So they would all end up in the same group. So we compile this whole group into a single class instead of 6 separate classes. And how do we generate the bytecode? For each common sub-expression, we'll just generate a function. And then we would rewrite the projection with the function. So instead of calling JSON parse, we will call the function that say get JSON parse. We'll generate a get JSON parse, and then all these other expressions will be rewritten to tricast get JSON parse function. You would say that, well, we are still calling it 6 times. Yes, so that's kind of wrapped inside of this function. So within this function, what we do is we basically introduce the flag and the results. So when the implementation of the function is basically, is this computed? If not, let's compute it. Otherwise, just return the stored results. And that way, at runtime, we would know that if it's not computed, it will come. So basically, the first time this function is called, it will compute the results, and all subsequent call will just get the reference. Yeah, so for that was like this is like kind of like the poster child example of like you get really a lot of benefit with actually like the whole algorithm that doesn't even need to work well to be able to handle this case. It's very simple. There's only one CSE and everything is combined in a group. But let's say a slightly more complicated example as in the expressions dependencies. Even though the data is actually quite simple. So this, we have 5 projections. X plus Y plus Z, X plus Y times Z, and then the same X plus Y plus Z times 2, and then cost the same as varchar, and then times 2 times Z. So there are a few, so one thing is X plus Y times Z doesn't share any common sub-expression with any other projections. So that would be one group. And all the other ones depend on X plus Y plus Z. So all the other ones would be in another group. And in this group, there's actually 2 common sub-expressions that depend on each other. The first one is X plus Y plus Z. And notice that there's actually another one that's X plus Y. But we kind of optimized that out because no expression depends directly on X plus Y. They at least depend on X plus Y plus Z. So we don't need to generate a separate function because function also has overhead. So we don't generate a function for X plus Y. We just directly generate X plus Y plus Z. And then the other one is X plus Y plus Z times 2. So this depends on the first CSE. So it basically would invoke the function for the first one to get the results and compute its results. And then we would have rewrite all the projections in terms of the first one would be just the first common sub-expression. And the second one is just the second common sub-expression. The third one is casting the first one to varchar, and the fourth one is the second one times Z. So that kind of like, so even if you have a dependency tree, you can still build a CSE this way. So let's see some results. There is a common sub-expression benchmark as a micro benchmark that's shipped together with the code. We did some very simple benchmarking. So here for big int, we basically did x plus y. I think for varchar, we basically did like the varchar version of x plus y. And JSON is a very simple JSON parse with A and B as like A1, B2 kind of like simple key value pair. And we can see that across the board, there's at least 10% performance improvements, even on a very simple, like if I have x plus y and another expression that depends on x plus y. So just by doing this on a very simple expression, we can still get some benefit. This is actually kind of a major concern because like when we were thinking about how to support this, it's actually very hard to quantify exactly how expensive operations are. And if you have a common sub-expression solution that only works for very expensive operations and not working, and so basically if you introduce a regression on very simple expressions, then it's actually very hard to roll it out or very hard to enable it by default. So basically it would be an opt-in instead of opt-out. So that's kind of partly why we decided to do it in bytecode generation, because in bytecode generation, if we do it, it's very unlikely to introduce large regressions. If you do a plan change, then like you potentially would introduce additional operators or additional page materialization and stuff, then it's harder to tell whether it would definitely introduce a benefit or not. So for the JSON parse, the original query with the 9 JSON parse, that kind of query, we do see 3x wins. Also, I mean, this is basically like if your query's major compute is spent on these very expensive kind of operations like parsing JSON or regex match, these very expensive functions, then your performance is going to just be like dividing how many times you're invoking them to the times of invocation, right? Like, so it's only 3x performance gain for that query because it does a bunch of other processing as well. If it's only doing JSON parse 9 times, it might be even better. So what are the downside? We do actually see some regressions with this. So one thing we see is that if you just end up with 100 expressions depending on the same, or like if you have like 100 projections, they depend on some CSE, compile them into the same class basically means you get a bigger class. And that at certain point can potentially trigger a large bytecode compiler failure. We kind of introduced the mitigation as, so like originally our implementation is pretty naive as we just partitioned the projections into the ones that depend on CSE and the ones that don't. And we compiled everything that depends on any CSE into one class. So after we see that, we basically decide, okay, let's just partition the projections by CSE. So only the projections that depends on the same set of common sub-expressions would be compiled in the same class. Well, that still doesn't quite cut it because I think especially for some Tableau generated queries or whatever, like you still have like, I don't know, 50 projections that depend on the same CSE. So, and then we also actually see a similar problem, or I mean like a problem that's triggered by similar features, which is that when the function is large, we think it's because the function is large, but basically the behavior that we see is that if you have like more than 20 projections, for example, if you combine more than 20 projections into the same class and generate one class for that and run that, somehow there's a wartime regression. It doesn't always end up with the CPU regression, but it always end up with the wartime regression. We suspect it's because maybe the code cache or something related to that. I didn't really dig into it, but we basically decided that with some micro benchmarking that 10 projections per group is pretty safe. So we basically arbitrarily say that we'll try to partition the projections by CSE, but then we'll cap it at 10. If it's more than 10, just split it into 2 groups or more groups if necessary. That way, I mean, within this group, you still get benefit of CSE, but then you don't need to pay the wartime regression. If anybody is interested in help us looking into why or what actually caused this, let us know. I would love to get the bottom of it. But like mostly by partitioning projections and limited to 10 projections per group, both of the problems largely go away. And if you still have an issue, there is a session property. You can turn this off. It's by default on. It's optimized common sub-expressions. Just set it to false, and that will turn it off. So, well, like obviously, common sub-expressions doesn't just exist in projection. They also exist in filter. Like one simple example is x plus y is larger than 10 and smaller than 100. And that x plus y it might be repeated twice. There are some like more like convoluted or like complex generated filter things that would have like if something is larger than 0 and larger than 0 and or something else. These kind of situations that happens a lot in complex query logic. So it's also beneficial to do this in filter. Filter is actually just a simpler case for compared to projection, because filter would always have at most one expression. So it's basically one expression. You are trying to find the common expression within that one gigantic expression. So yeah, and what's next? So we basically only have done this in page function processor, which is used when the input is a Presto page. That's the case for all the like non-leaf project, or like any project that's not directly on top of scan would all use page function processor, page function compiler. So it covers most of the cases. Interestingly, with ARIA scan, we've been trying to push more complex logic to scan, which exposed us to this problem that some expression that we push down to scan can be quite complex and still have common expressions as a result. So we also want to do this in cursor processor compiler. Unfortunately, so basically the difference between page function compiler and cursor processor compiler is the input is a page, as it's a column-oriented format. The Presto page is basically grouped, organized by column blocks. And the cursor processor compiler, because it's kind of tied more into the connector and the data, so a lot of the connector have it as a record oriented, so it's a row oriented format. That's why like the function APIs are slightly different, so the bytecode are generated separately. Yeah, so this is, I think, like a lot of the code are already out in 2.35. There are some bug fixes and improvements that's in 2.36. So you can already start using it, and if you see any problems, just let us know, create an issue or like ping us on Slack or anything. Yeah, that's all of my talks. Any questions?
I see a couple of questions wrong, so let me read them out. The first question is from Devesh from Databricks. So Devesh says, this is really cool, but I didn't fully understand why this was done at the page function compiler versus at the analysis and planning time. Is it because the overhead of the additional buffering you would need to implement the common sub-expression optimization? Thanks.
Yes, so that is one of the reasons. So there are actually two reasons when we start thinking Presto planner and optimize. The rules kind of assume a certain orders, right? Like if we do it in the planner, we have to do it at the end of query planning pretty much, because certain optimization rules will try to enroll. Like basically, if you do it at planning, you're breaking a projection into multiple projections depending on each other. And you at the same time, you might have optimization rules that try to inline them. Because inlining can potentially push down things further. So the rules actually don't necessarily work with each other. So you have to figure out what's the order of applying the rules. And so the safe place is towards the end. That's kind of, so if it's towards the end, then you pretty much only work within a project. And you don't really have this like overall like global view of things anymore. And then like the second is basically if we're breaking it into multiple projects, then in between projections, you're basically writing it into a page and read it out of a page again. So there are overheads to that. Yeah, so both of these. And another thing is we wanted to do this as part of like a COVID-19 response for fast, and we figured that if we do it in bytecode generation, it either works or it doesn't work. It's very unlikely to trigger some like corner case that like weird bugs, because normally bytecode generation bugs tend to surface them pretty quickly. That's our concerns. Yeah.
Next question is from Karthik from Uber. Karthik asks, are UDFs also considered for common sub-expression evaluation?
Yes, so in general, all the operators are functions. And if we're talking about the SQL UDFs are also compiled or handled within the engine. So yeah, that would also be considered as like yeah. So if you depend on the same SQL function, then that SQL function would only be called once.
Cool. So I see no more questions, but I have one question from my side. So you mentioned briefly that you folks are also considering updating it in the on the scan operator also, right? In the cursor class. So do you have any idea on when you guys might be able to put something out into open source?
Yes, that's I hope sometime soon. It's actually not hard to do. So if anybody in the community is interested in doing this, the cursor processor compiler and the page function compiler, if you look at them, the implementation are quite similar. There are two different functions because the APIs are different. So basically, how like project operator invoke them are different because the data layout is different, but the actual compilation of the code is the same. So basically, we just need to hook the same logic into a different API. So it's not a lot of work. I'm inclined to have someone else working on it right now because it's a good opportunity to actually learn about bytecode generation and ramp up on Presto. So we were hoping to kind of give it to a new team member, or if anybody in the community want to learn about bytecode, we also welcome their contribution on that. Just talk to me and we can work on that.
Awesome. That's great, Rongrong. I think that's a great approach to this. I think if somebody else can take this on, it'll definitely be a good contribution to the community. So I think that's it for questions and answers today. Thank you all for joining us for our meetup today. Thanks to both our speakers, Vala and Rongrong. These were great talks. We have recorded them, and if your colleagues were unable to attend it, or if you yourself want to review this again, we will be putting out a recording in the next few days. Please keep an eye on the meetup page. Also, if you have any other topics that you want to hear about from Presto engineers, please share that to us on the meetup page, and we'll try to see if we can arrange some talks in those topics in our subsequent meetups. Thanks again, everybody. Thanks for joining us, and hope to see you all soon in our next meetup. Have a great weekend. Thanks. Bye.